Welcome to another episode of My Weird Prompts, an AI-generated podcast featuring the random prompts of Daniel Rosehill as answered by a revolving cast of friendly AI characters. Join us for deep dives into AI, technology, and whatever other random thing Daniel finds fascinating today. Subscribe on Spotify or your favorite podcatcher. Now, today's episode.
My Weird Prompts is an AI-generated podcast produced by Daniel Rosehill, a verified human with documentation to prove it. While every effort is made to ensure our AI hosts draw from credible sources and run on cutting-edge models, they do occasionally make things up with alarming confidence. As with everything in life, and especially this podcast, treat all claims as spurious until confirmed to be not. Daniel, Herman and Corn accept no responsibility for any decisions made based on the confident ramblings of our artificial presenters. Now, today's episode.
Hello there, Herman and Corn. So, I was recently taking stock of the different types of multimodal AI model that is capable of processing audio as a modality. And I've doing a lot of work and research into the idea of multimodal AI and a particular use case, and trying to sort of evaluate whether audio multimodal models could be a better fit for a task than the more traditional ASR models for speech recognition. And in the course of looking through these models, I came across some Omnimodals, and I said, that's really interesting. There is a task classification on Hugging Face called any to any, and just as the name suggests, these are models which support any input format and any output format. So rather than having a model that can take audio, it can process audio as well as text. This can do the full gamut. You can send it a simple text prompt, you can add an image, so it's kind of a vision model, you can add an audio file, and you can mix and match, which creates, each of these really creates a whole world of workflows. But when you sort of stretch it out to Omni, you really get an awful lot of things. And of course, the output format in turn also enables a lot of workflow. So Omni is kind of the far end of it can do anything. And when I was looking at the implementation papers on Hugging Face, which is kind of where there's a line between where geeks at my level of geekery have to sadly drop off, and the real hardcore, ML PhDs sort of do their thing. And I was trying to understand that level of it, where they were explaining the actual tokenization process by which these different modalities are handled. And that's what I'd love to get into in today's podcast. When we talk about throwing different formats at a large language model or an AI model, we talked before about text tokenization, the process by which texts are converted into vectors and sent to a model for inference, and how statistical prediction happens, and then we get output, which I guess is also vectors getting turned into text so that we can read it. And what I'd be really interested to learn about is how that works for something like video or images, which, just thinking out loud, it seems like we're used to thinking about images as vision language models as kind of pretty basic, right? It's been a while since ChatGPT supports that. I think it even always did. But even if I send a photograph of a can of beer against a white background, that might seem like a really basic photo, but there's a lot of data in that image, more so than text. And when we talk about audio, we're talking about a lot of data representing speech. And when we talk about video, we're talking really, really at the kind of far end of complication, where we're sending a large amount of data with 24 potentially different images every second, and asking it to understand based on that. And of course, then we have real-time video, but let's just talk about non-real-time for the moment. That process by which these non-textual data forms go through the same model, how does that work exactly? And how much more complicated is it for a model to handle these? And it seems to me remarkable these multimodal models maybe are the kind of forerunners of where we're going to go. But how are this emerging breed of models able to tokenize all these forms of data?
Welcome back to My Weird Prompts, the podcast where we take the fascinating ideas sent in by our producer Daniel Rosehill and really dig into them. I'm Corn, your co-host, and as always I'm here with Herman Poppleberry.
Hey everyone, great to be here. And I gotta say, today's prompt is exactly the kind of thing that gets me excited because it sits right at this intersection of practical AI work and some genuinely deep technical complexity.
So Daniel sent us this really meaty question about multimodal AI models. Specifically, these omnimodal models that can handle any input and any output format. And he's curious about how tokenization actually works when you're throwing all these different data types at a model. Images, audio, video, text, all mixed together.
Right. And here's what I think is important to understand from the start. Most people think of AI models as just text machines, right? You type something in, text comes out. But what's happening now is we're moving toward these systems that can genuinely handle anything.
Which is kind of wild when you think about it. Like, I can understand how text becomes numbers. We've talked about that before. But when you're talking about an image or a video, that's a lot more information to encode, isn't it?
Exponentially more, actually. And that's where the interesting technical problem emerges. So let me set the stage here. Traditional tokenization for text is relatively straightforward. You take words or subwords, you assign them numerical values, and the model processes those sequences. But when you start adding images or audio...
Wait, but before we go too deep, I want to make sure I'm understanding the scope here. When we talk about these omnimodal models, are we talking about models that are brand new? Or are we talking about an evolution of things like GPT-4 vision that already existed?
Good question. So there's definitely been a progression. GPT-4 vision and similar vision language models have been around for a while. You're right that ChatGPT has supported image input for quite some time. But what's changed recently is the explosion of truly any-to-any models. Models like Qwen 3 Omni and 5.4 that came out more recently can handle audio, video, images, text all at once, and they can output any of those formats too.
So it's not just about accepting multiple inputs. Anymore, it's about accepting any combination and producing any output.
Exactly. That's the real shift. And the reason that matters is because it opens up entirely new workflows. You're not locked into image in, text out, or audio in, text out. You could theoretically do audio in, video out with text annotations. You could mix modalities in the input itself.
Okay, so that's the business value proposition, I get that. But the technical question Daniel was really interested in is, how do you actually make that work? How do you take something as different as an image and audio and convert them into a format that the same model can process?
Right, so this is where tokenization becomes the key. And I think the best way to understand this is to start with what we already know works for text, and then understand how it scales to other modalities.
So, text tokenization, we've covered this before, but for people who didn't hear that episode, can you give the quick version?
Sure. A language model doesn't actually understand words the way you and I do. It breaks text down into tokens. Could be whole words, could be subwords, could be individual characters depending on the tokenizer. Each token gets assigned a number, and that number maps to a vector in high-dimensional space. So the word hello might become token 1534-2, which then becomes a vector of, say, 768 or 2048 numerical values depending on the model size.
And those vectors encode meaning somehow.
They encode statistical relationships. The model learns that certain tokens tend to appear near certain other tokens, and those patterns get baked into the vector space. So king minus man plus woman gets you close to queen in that space. It's not that the model knows what a king is, it's that it's learned the statistical patterns.
Okay, got it. So now when we move to images, we can't just do that same process, right? Because an image isn't a sequence of discrete tokens the way text is.
Exactly. An image is a continuous grid of pixels, each with color values. And here's the problem. If you tried to tokenize an image the same way you tokenize text, treating each pixel as a token, you'd have millions of tokens just for a single photograph. That's computationally infeasible for current models.
Oh wow! So that's why you can't just throw raw pixel data at these models?
Right. So what researchers do instead is they use what's called a vision encoder or an image encoder. This is typically a convolutional neural network or a vision transformer, something like CLIP, or similar architectures that were trained specifically to understand images. That encoder compresses the image down into a smaller set of tokens that capture the important visual information.
So you're pre-processing the image before it even gets to the main model?
Yes, exactly. The image encoder does a kind of semantic compression. Instead of having millions of pixel-level tokens, you might end up with, say, 100 or 200 visual tokens that represent high-level feature shapes, colors, objects, spatial relationships, all that stuff.
But I'm wondering, doesn't that lose information? Like, if I have a really detailed image, you're compressing it down significantly. How does the model maintain understanding of fine details?
That's a fair pushback, and honestly, it's one of the limitations we're still working with. Different models handle this differently. Some use hierarchical encoding where you maintain multiple levels of detail. Others use adaptive token allocation. The model learns to use more tokens for complex regions and fewer for simple ones. And some newer approaches, like what you see in models that support higher resolution images, use tiling or patching strategies where they break the image into smaller chunks and encode each chunk separately.
So there's definitely a trade-off happening there between computational efficiency and detail preservation.
Absolutely. And that's where design choices really matter. A model optimized for speed might compress more aggressively. A model optimized for accuracy might preserve more tokens, which costs more computationally, but gives better results.
Okay, so we've got images figured out conceptually. Now let's talk about audio, because Daniel mentioned that seems like another whole level of complexity.
Audio is actually fascinating because it's different from images in an important way. Audio is inherently temporal, it's a sequence like text. But it's a continuous signal, not discrete tokens, so you can't just break it into chunks the way you'd break text into words.
Right, so how do you handle that?
Well, typically audio gets converted into a spectrogram first. That's essentially a visual representation of audio. It shows frequency content over time. You can think of it as kind of like a sheet music representation, where the vertical axis is frequency, and the horizontal axis is time, and the brightness shows intensity.
Okay. So you're converting audio into something more image-like.
Exactly. Once it's a spectrogram, you can apply similar techniques to what you do with images. But there's another approach. Some models use raw audio waveforms and apply special audio encoders trained on speech or music. Models like Whisper, for example, can process raw audio directly and encode it into tokens.
So there are multiple ways to handle audio depending on what you're trying to do?
Right. If you're doing speech to text, you might want to use an ASR optimized encoder. If you're doing general audio understanding, you might use something more general purpose. The point is, you're converting that continuous audio signal into a manageable number of discrete tokens.
Let me make sure I understand the data volume here. Daniel mentioned that a photograph might seem simple but contains a lot of data. Can you put that in perspective?
Sure. A single photograph might be, say, 3,000 by 2,000 pixels. That's 6 million pixels. Each pixel has 3 color channels, red, green, blue, so that's 18 million individual numerical values. When you compress that through a vision encoder down to, say, 576 tokens, you're reducing it by a factor of about 30,000 to 1.
Wow, that's aggressive compression.
It is, but the magic is that the encoder learns to preserve the important semantic information. You lose pixel-level detail, but you keep object identity, spatial relationships, colors, compositional, the stuff that matters for understanding the image.
And audio?
Audio is actually even denser in some ways. A minute of audio at CD quality is about 10 million numerical values. When you convert that to tokens, you might end up with a few thousand tokens depending on the model.
Okay, so now video. Daniel mentioned this as the far end of complexity to 4 frames per second, potentially, all encoding different information.
Yeah, video is where things get really intense. Let's say you have a 10-second video at 24 frames per second. That's 240 frames. If each frame is a 3,000 by 2,000 image, you're looking at millions of frames worth of data. That's computationally massive.
So, how do models actually handle that?
There are a few strategies. One is temporal compression. You don't encode every single frame. You might encode every fourth or eighth frame, or you use keyframe detection to identify which frames are actually important. Another approach is to use a video encoder that's specifically trained to understand temporal information, so it can compress not just spatial information, but also temporal patterns.
Like, it understands that if a ball is rolling, the next frame will have it slightly displaced.
Exactly. The encoder learns temporal patterns motion, object tracking, scene changes, all of that, so it can encode that information more efficiently than if it was just treating each frame independently.
But here's what I'm wondering, and I think Daniel was getting at this, Towen. You have all these different modalities coming in. How does the model actually know how to process them together? Like, you've got these different encoders for different input types. They all spit out tokens. But then what?
Right, so this is where the architecture gets really interesting. Most of these multimodal models use what's called a unified embedding space. All the different encoders to text tokenizer, the image encoder, the audio encoder,
So they're all speaking the same language at that point?
basically, yes. It's like they're all translated into a common currency. The embedding space is the currency. A visual token might be a 2048 dimensional vector, and a text token is also a 2048 dimensional vector. They're different tokens representing different information, but they can coexist in the same model.
That seems kind of magical, honestly. How do you even train a model to do that?
Well, it's not magic heights, it's a lot of data and careful engineering. The training process typically involves multimodal datasets where you have examples of text paired with images, images with audio, audio with text, and so on. The model learns the statistical relationships between these modalities.
But wait, that's where I want to push back a little bit. Daniel asked specifically about these any-to-any models, these omnimodal models. When you're supporting truly any input and any output, you're not just talking about having encoders for different inputs, right? You also need decoders for different outputs.
Yes, and this is where it gets more complex. You need not just encoders, but also decoders, or, more accurately, output heads for each modality you want to generate. So if you want to output audio, you need an audio decoder. If you want to output video, you need a video decoder. These are often based on diffusion models or other generative architectures.
So the core model is kind of this central hub that takes in any modality and outputs to any modality, but it's surrounded by all these specialized encoders and decoders?
That's a reasonable way to think about it, though some newer approaches are trying to move away from that architecture. Some of the really cutting-edge omnimodal models like Qwen3 Omni are trying to have more unified tokenization schemes so that you don't need as many specialized modules.
Okay, so let me ask you this. How does that unified tokenization actually work? Because that seems like the hard problem. Text is discrete, images are continuous spatial data, audio is continuous temporal data. How do you find a common representation?
This is genuinely one of the hardest problems in AI right now. Different approaches are emerging, and I don't think we have a perfect solution yet. One approach is to use vector quantization. You take any input image, audio, whatever, and you convert it to a continuous representation, then you quantize it into discrete codes. So an image becomes a sequence of codes, audio becomes a sequence of codes, and the model processes codes universally.
So you're forcing everything into a discrete code-based representation.
Right. The idea is that if you can represent all modalities as sequences of discrete codes, then the problem reduces to sequence modeling, which transformers are really good at. You've essentially converted the multimodal problem into a translation problem.
But doesn't that lose information? Like, if I'm quantizing audio into codes, I'm losing the continuous nature of the signal, right?
You are losing some information, but the question is whether you're losing information that matters. If you have enough codes and they're chosen intelligently, you can preserve the perceptually important information. It's a similar trade-off to what we discussed with images.
Let's take a quick break from our sponsors.
Tired of your tokens being disorganized? Introducing TokenFlow Pro. Revolutionary neural organization system that uses quantum-aligned code clustering to optimize your modality compression ratios. Whether you're processing images, audio, or video, TokenFlow Pro analyzes your data streams in real time and automatically redistributes your computational load across 47 different dimensional planes. Users report feeling more efficient and experiencing what they describe as improved tensor alignment. TokenFlow Pro also comes with our exclusive Mind Meld Accelerator, which you absolutely do not need to understand to benefit from. Side effects may include unexplained confidence in your AI infrastructure and an urge to tell people about dimensional planes at parties. TokenFlow Pro. Because your tokens deserve better. BUY now.
Thanks, Larry. Anyway, where were we? Right, so we're talking about this quantization approach. But I'm curious, when you're dealing with real-time video or real-time audio, does this approach still work? Because Daniel mentioned real-time as being even more complicated.
Real-time is a completely different beast, yeah. The latency requirements are much tighter. You can't do heavy compression or complex encoding if you need to process and respond to video or audio in milliseconds. So real-time multimodal models typically use lighter weight encoders, and they might process data in a streaming fashion rather than waiting for the entire input.
So they're making different trade-offs?
Absolutely. For non-real-time work, you can afford to be thorough. You can do complex encoding, preserve lots of detail. For real-time applications, you have to be fast, which means you sacrifice some depth of understanding for speed.
That makes sense. But here's what I'm still not totally clear on. When you have this unified embedding space where all modalities are represented as tokens, how does the model actually learn the semantic relationships between them? Like, how does it learn that the word dog and the image of a dog and the sound of barking are all related?
That comes from the training data. If you train on datasets where you have images of dogs paired with the text dog and audio of barking, the model learns those associations. The embedding space naturally develops so that semantically related tokens end up close to each other.
So it's learning through exposure to paired examples.
Yes, and this is why having good, diverse, multimodal training data is so important. If your training data is biased or limited, the model's understanding of cross-modal relationships will be too.
I want to push back on something you said earlier, though. You mentioned that some of the newer models are trying to move toward unified tokenization schemes to reduce the number of specialized modules, but I'm skeptical that you can actually do that effectively. Don't different modalities have fundamentally different characteristics that require different handling?
That's a fair point, and I think the reality is more nuanced than I made it sound. You're right that images and audio have different properties, but the idea isn't that you use identical processing for everything, it's that you use a unified framework that can be adapted for different modalities. Like, a transformer can process text, images, audio, video. The core architecture is the same, but you might adjust the input encoding and the output decoding.
Okay, so it's more about unified architecture rather than unified processing.
Right? The transformer's strength is that it's agnostic to the type of sequence it's processing. Give it a sequence of tokens, it'll process it. Those tokens could represent text, images, audio, whatever.
That actually makes more sense. So the real innovation is finding ways to convert different modalities into token sequences that the transformer can handle.
Exactly. And different teams are experimenting with different approaches. Some use vision transformers for images, audio transformers for audio, and they all output to a common token space. Others are trying to develop more unified encoding schemes. It's an active area of research.
Let me ask you a practical question. If I'm a developer and I want to use one of these omnimodal models, what am I actually dealing with in terms of implementation complexity? Is this something that's accessible to people who aren't deep ML researchers?
Well, it depends on what you're trying to do. If you just want to use an existing model like GPT-4o or Qwen3 Omni through an API, it's pretty straightforward. You send in your multimodal input, you get back your output, the complexity is abstracted away.
But if you want to fine-tune one or understand how it works under the hood,
then you're getting into the weeds pretty quickly. You need to understand how the different encoders work, how to handle the token sequences, how to manage the computational load. It's definitely PhD level stuff if you want to do it from scratch.
which is kind of what Daniel was pointing out. There's this line where the documentation on Hugging Face goes from geek accessible to real hardcore ML researcher territory.
Yeah, and I think that's actually a sign of healthy development in the field. It means there are tools at different levels of abstraction. You can use these models without understanding the deep internals, but if you want to, the research is available.
All right, we've got a caller on the line. Go ahead, you're on the air.
Yeah, this is Jim from Ohio. So I've been listening to you two go on about all this tokenization business, and I gotta say, you're overcomplicating it. Back when I was working in IT, we didn't need all these fancy encoders and decoders and embedding spaces. You just moved data around.
Well, I appreciate the perspective, Jim, but I think the difference is that back then you were moving data around without trying to extract meaning from it. These models are trying to understand the content.
Yeah, but that's exactly what I'm saying. You're making it too complicated. My neighbor Dennis has a camera system that processes video just fine, and he didn't need any of this quantum code clustering stuff or whatever. Also, it's supposed to snow here in Ohio next week, which is ridiculous for October. But anyway, the point is, can't you just convert everything to the same format and be done with it?
I mean, that's kind of what we were saying, Jim. You do need to convert things to a common form of tokens, but the trick is that you can't just convert an image to text or vice versa without losing information. You need these intermediate representations.
That doesn't sound right to me. In my experience, computers are pretty good at converting between formats. Why is this different?
Because you're not just converting format, you're preserving meaning. You could convert an image to text by just listing pixel values, but that doesn't preserve the semantic meaning, the fact that you're looking at a dog, for instance. These encoders preserve that semantic information while reducing the data volume.
I guess I can see that. Still seems unnecessarily complicated to me, though. Anyway, thanks for explaining, I guess. My cat Whiskers is staring at me weird right now, which is concerning. But yeah, I'm not convinced you need all this complexity, but I'll take your word for it.
Thanks for calling in, Jim.
Yeah, no problem. Keep up the podcast or whatever.
So one thing that's worth thinking about as we wrap up is how this tokenization approach might limit or enable different kinds of AI capabilities. Because the way you tokenize something fundamentally shapes what the model can learn about it.
How do you mean?
Well, if you have an image encoder that's trained to recognize objects, it might not be great at preserving artistic style or subtle color information. So if you use that encoder for an image-to-text model, it might describe what's in the image but miss the artistic aspects. But if you use a different encoder trained on art history data, you get different strengths and weaknesses.
So, the choice of encoder is really consequential?
It is, and I think that's one reason why we're seeing a lot of research into more flexible, adaptive encoding schemes. Models that can learn what level of detail to preserve for different types of inputs.
That's fascinating. So the next generation of these models might be smarter about how they tokenize things based on the task.
Potentially, yeah. Imagine a model that recognizes, I need fine detail for this part of the image, but I can compress that part more aggressively. That's the kind of adaptive intelligence we might see emerging.
So going back to the original question, Daniel asked, is audio tokenization harder than image tokenization?
They're hard in different ways. Images are spatially complex but static. Audio is temporally complex but one-dimensional. Video combines both spatial and temporal complexity. I wouldn't say one is strictly harder than the other. They're different problems.
But from a practical standpoint, if I'm building a multimodal model and I have limited computational resources, should I prioritize supporting certain modalities over others?
That's a good question. I'd say it depends on your use case. If you're building something for content creators, video support might be critical. If you're building something for accessibility, audio might be the priority. There's no universal answer, but the bottleneck is usually computation and data.
Speaking of which, one thing I'm curious about, all these encoders and decoders, all these different models working together, that's a lot of parameters. How big are these omnimodal models compared to text-only models?
they're significantly larger. A text-only model like GPT-3 was 175 billion parameters. Some of the newer multimodal models are in that range or larger, but they have to distribute those parameters across handling multiple modalities. So you're not necessarily adding 75 billion parameters per modality they're sharing and efficiency gains, but you're definitely not staying at text-only sizes.
So there's a real computational cost to this multimodal capability.
Absolutely. Training these models is expensive. Inference is expensive. There's definitely a trade-off between capability and efficiency.
But you think it's worth it?
I do, yeah. Because the capability gains are significant. Being able to process any modality opens up entirely new use cases. And as we get better at tokenization and encoding, we'll get more efficient.
All right, so what's the practical takeaway here for listeners? If you're working with AI and you're thinking about using multimodal models, what should you actually know?
I think the key thing is to understand that multimodal models aren't magic. They work by encoding different data types into a common token space, and there are real trade-offs in that encoding process. When you're choosing a model, you should think about what modalities you actually need and what kind of fidelity you need for each.
And if you're curious about how this actually works under the hood,
then you have to be willing to go deep. Read the implementation papers, understand the architecture choices, maybe try implementing something simple yourself. It's complex stuff, but it's not impenetrable if you're willing to put in the effort.
What do you think comes next? Where is this heading?
I think we're going to see more unified architectures that can handle multiple modalities more seamlessly. I think we'll see better encoders that preserve more semantic information while being more efficient. And I think we'll eventually see models that can generate novel combinations of modalities like generating video with a specific audio track that matches it semantically.
That's wild. Like AI that understands that the audio and video need to be coherent with each other?
Exactly. We're not quite there yet, but the pieces are in place.
Well, this has been a fascinating deep dive into how these models actually work. Thanks to Daniel for sending in this prompt. It's exactly the kind of thing that really gets into the technical weeds, but is genuinely important for understanding where AI is heading.
Yeah, and I think what's cool is that this is happening right now. These models are being developed and refined as we speak. A year from now, the landscape might look pretty different.
You can find My Weird Prompts on Spotify and wherever you get your podcasts. Thanks for listening, and we'll catch you next time.
See you next episode.
Thanks for listening to another episode of My Weird Prompts, an AI-generated podcast featuring Daniel Rosehill's AI prompts as answered by a revolving cast of friendly AI characters including me, Cornelius the Sloth. Subscribe on Spotify or visit myweirdprompts.com.